Ready? Let's give you the last problem of the day for me. Probably first problem of the day for you. Who knows? This is a textbook problem of Physics 2, where we are asked to find the x and y components of the electric field at a point at a specific point that is a perpendicular bisector. Okay, perpendicular bisector of a charged rod with uniform density of charged particles. Okay, so it's got a uniform distribution of the of charge 8 picocoulombs. It looks like 800. It's 8.00 picocoulombs. Let's see how is the book put it. Yeah, it's there's a positive charge of 8.0 picocoulombs spread uniformly along the thin, non-conductive rod of length. Okay, the length is right there. Of length. Why did I put 13? It's 16. Okay, here we go. Of length 16 centimeters. Well, what are the x and y components of the electric field produced at point P at a distance of 7 centimeters? Right there. From the rod along its perpendicular bisector, meaning that the point at which we're measuring is perpendicular to the rod, but not only that, it's at the center. It's at a perpendicular bisector. The line from the point of measurement to the rod is perpendicular to the rod, and it's like it bisects it through the middle. Hopefully that makes sense. All right, let's get with this problem. So we're going to use this formula here. Okay, let me kind of go over here. Okay. Oh yeah. Also, because it's a textbook problem, here's the answer. It's 9.66. Can be approximated to 9.66 Newton over coulombs. Okay. Or also referred to as, let me just make sure here. Also referred to as volt per meter. Okay, newtons over coulomb or volt over meter. Let's get it. So we're going to use this right here. So E is equal to, okay, coulomb's constant times the charge over our distance squared. Okay, so how far are we from the charged object? In this case, the charged particle. How far are we from it? Square it. With this problem is also useful to because the charges are evenly distributed through the rod. We can use the linear density. Okay. So we can use a linear density here, which is equal to Q over L. Okay. Because this is a charged rod, it's not a particle. It's got many little particles inside of it. We can say that there's an infinitely amount of small charged particles inside of it. So let me use a little thing here. use the blue one. Yeah, this little small little section here, we can say that's one particle. It's infinitely small, so we call it dq. Okay, dq. Let me make that more apparent. That there, dq. And then over here we can say dq, okay, is equal to the linear charge density times an infinitely small length. Okay, so x, the interval being teeny tiny, infinitely small, dx. Okay. Okay, so all right, so first thing, we well, we're gonna make this into an integral type thing. So we're gonna say that dE, okay, is equal to, okay, dq. Okay, we're gonna bring that in here. Then r squared. We have to figure out what our r squared is. Okay, so all right, so we're gonna look at the point P. Okay, we have a distance r from the rod. Okay, we have all these charged, these positively charged particles. Okay, all right, and essentially, if we draw the vectors, that will be a product of this calculation here. So that the distance, okay, of the charged particle to the point P, and that'll create an electric field. Okay. The reason it's going out is because we assume that this test, we imagine a test charged particle here being positive. So if there's a charged particle that's positive and you have a positive charged particle, it's going to tend to go outward, okay, away from it. All right, I move this r over here. Okay. So now we have a triangle, and this is a perpendicular bisector. It's 90 degrees. It's perpendicular to the rod. This is a right triangle. We can use Pythagoras theorem. Okay, so Pythagoras theorem right here. A squared plus b squared is equal to c squared. All right. In this case, this side is our r. All right. This is little r. All right. Okay, because we're making the connections. All right, and then this bottom one is going to be x, right? This bottom one's going to be yeah, x. There you go. This bottom's going to be x. And yeah, so if we replace these values with now what we have here, so x squared plus r squared, okay, it's going to be equal to the hypotenuse, which in this case is r. All right. So literally we end up with r squared. So we don't even have to do any algebra here. We can just substitute this expression into there. X squared plus r squared. All right. That takes care of this side of the equation. We also have to think about dE. Okay. Well, what is dE? All right. All right. So that takes care of that. in mind, we're gonna, when we set up this integral, so like our end product, right? Well, what's the end, right? We want to be able to have a 0 at the bottom, right? So we're going to be adding up from 0. We're going to go all the way to the end of the rod. Because this is directly in the middle, we can say that okay, this part here is equal to L squared. It's equal to half the length of the entire rod. Okay? And so does the other side. All right? So in doing that, if we go from 0 to L squared, okay, from here to there, like this will be the whole integral. And then by symmetry, we're going to just assume that if we multiply this integration here by 2, we will get the other side of the rod by symmetry, the argument being symmetry. So we put a 2 in front of it. There's definitely going to have a 2. There's definitely going to be a 2 constant. So we're going to add this 2 here. Okay. Also, we can say that, let me keep on the point here. So we can say that, here we go, perpendicular bisector, this is a rod, positive charges. Okay, is that on that? Yep. Okay, so we can say that as we do the integration, okay, we're going to end up with infinitely many vectors, okay, pointing away from our charged rod, right? We're going to have infinitely many, okay, many. Imagine there being an infinite amount of arrows, okay, infinitely many. So yeah, imagine there being an infinite amount of vectors pointing this way, kind of like pointing upward, and as you integrate through the rod, okay, as you go through, all right, you get all these electric field vectors. So let me make sure I'm recording. Yep. So just for the sake of explaining this, I'm going to minimize the amount of vectors there are. But you know now that there's going to be an infinitely many amount. Okay. All right. So the question here asks, what is the x and y component of the E field at point P? So the components of a vector are, so if this is one vector, right? Let me make sure to draw it very neatly, very bold, so it comes across in the video. Okay. Okay, so say this is your E vector. Okay. Its x component will be, therefore, the x component of the vector will be a length that shows the horizontal coverage of the vector, because the vector is at an angle, right? It's at an angle, so an x component will show the coverage in the x-axis, okay? The coverage of the vector. The y component will show the y coverage of the vector that's at an angle, right? And just for funsies, let me shift this vector up just so that we can make a triangle. Okay, you can do that, right? This is the x component, this is the y component, all right? Hopefully that comes across the video. So say we add up infinitely many vectors. Say this is the okay, say the rod is over here, right? Charged particle. Say there's this one here. Okay, another charged particle. All right. So say this is the beginning of the rod, and this is the last piece of charge on the rod. Okay. If we look at the x components of both of these vectors, okay, you can see that one is going this way and the other one is going the other way. Meaning they're going to cancel out. They're going to cancel. Say that this is an equal amount of length from the center to this part over here, which is an equal amount of length from the center. Okay, L over 2, okay, this area here, negative L over 2, and this part over here being positive L over 2. This will create the same magnitudes, all right? The magnitude of the vector will be the same. And thus the x components, because they're looking opposite directions, they're going to cancel out, okay? It's like saying 1 plus minus, it's like saying negative 1 plus 1 is equal to 0, right? So with this problem, we see that the x components will equal to 0. So the first part of this problem will be 0. So x components will be equal to 0 newtons per coulomb. All right. We've answered the first half of the question. The second half of the question, being like, all right, the y components. It doesn't seem like all the arrows are going to be pointing upwards. There's no arrows that are going to be pointing downwards. Okay, because for the entirety of the rod, this is a positive charged particle, and the entire rod is positively charged. So the charge, the test charge, which is positive, is going to want to be going in the opposite direction of the rod. Okay. Therefore, we can say that yes, every single y component will add up. Okay. So just to put it more explicitly, say this blue arrow here is the y component for this vector. This red y component is going to be the y component for this vector here. They're both going in the same direction, therefore they will add up. Okay, it's like saying 1 plus 1 equals 2. All right. The theory, there being said, okay, the theory there being said, we need to account for the summation of the infinitely amount of y components that will arise from this computation. Okay, infinitely many, and I drew these arrows upward, separated from each other, but just know they're all concentrated into this point. Okay. All right, let's do that. So again, we have our charged rod. It's distance r from the charged rod. We have a distance r from the point P. Okay. And in order to add up all of the y components, we need to know what is a y component. Okay, like mathematically speaking. Okay, so say we have this charge here and this charge over here. Okay. we can measure this angle. Okay, we can. Okay, and if anything, the only angle that would be changing would be this one here, because the summation implies that we will be just moving in across the entire rod. Okay, so we will be, well, in this case, we will be starting out here and increasing the angle from point P to the rod. Okay. Therefore, the angle is going to be changing. It's going to be this one. Okay. There being said, this is our point P, and this is our, if this is the length that we're measuring, the vector is going to go that way, and our y component is going to do this, and our x component it's not going to matter for this problem, but at least let's just put the triangle here, just to complete the triangle. Okay, let's just put the x component here to complete the triangle. So what is, the question that we're asking here is, what is this length? Okay, what is that? What is this length? So we know that whenever we have two perpendicular lines that are crossing each other at an angle, the angle itself also it gets mirrored into the other side. Okay. And now, if you were to say this is x and this is y, right? Or we need this to be our y vector, and this is our x. Okay. Y component, x component. Oddly enough, for this problem, because the angle is at this point of the triangle, the component that we're measuring is adjacent to the angle. So meaning that the y component is going to be equal to the magnitude of the resulting vector, the magnitude of it, times cosine of theta. Okay, times cosine of theta. Cosine of theta being here. Okay, cosine of theta. And because we're doing the summation from this point here outward at an angle outward, and then we're multiplying the mirrored side of the rod, we're going to put this 2 up here. Okay. So now now that we've talked about that, the theory behind it, we don't just leave cosine of theta. We don't know the angles that are happening or anything like that. We do know what is cosine of theta. Okay, so let's do that. Let's do that. Okay, let me remove the 2 out of here. So I was trying to make a point back then. We have it over here. Let's not confuse ourselves. You know what? No, I'll leave it there, and I'll take the 2 out of here. Because here we're just looking at the y component, right? Yeah. Okay, so our y component is equal to the magnitude of the resulting vector, and then our cosine. Okay. What is cosine equal to? Well, in this case, right, we have our cosine is equal to the y length here, okay, over No, that's not a good way to put it. The good way to put it is that when you're measuring from the rod, okay, this is the theta we're measuring. We know that it mirrors to the other side. And so we know that our the length isn't changing, at least for this bottom part. So we can say that r, okay, cosine is equal to adjacent over hypotenuse. Okay, adjacent to the angle, okay, and then hypotenuse being this side here. Okay. So now for the hypotenuse, we do have to, because the hypotenuse is essentially asking like for r, just r. So we had figured out the equation here, which was r squared is equal to x squared plus r squared. Okay. But because we just want the hypotenuse, which is just r, we have to take the square root over here, get rid of that, so we could then just have r by itself, and then we just have x squared plus r squared. We can also rephrase the square root of x squared plus r squared as x squared plus r squared, both of them to the power, parentheses x squared plus r squared to the power of 1 over 2. Okay. And then our adjacent would be r. Okay. It would be r. That way we don't have to talk about angles or anything. We just know that as x changes, this is the changing factor of this equation. As you start summing more and more of these charged particles, your x will change. That is the part of it that's changing. So as that changes, the angle increases, and we're able to peer into what's happening over here on this top part of the P point. All right, so that being said, now we arm this integral. Okay. Now we arm this integral. So the integral is going to be 2 dE cosine of theta, okay, which is equal to. Let me put this right over here on this side. Okay, yeah, 2 dE cosine of theta. All right. We spend all this time defining what is dE, what is cosine. Okay. And also we've explained why we're doing the integration 2 times. Okay. Okay, so now we have two things. We have 2. Okay, we have our dE. Okay, which is right there. Okay, dq over x squared plus r squared. Okay. And then we have our cosine here, all right, which is defined right here. R squared over x squared plus r squared. No, it's up top. It's not r squared. It's just at the bottom. Over 2. All right, now let me clean this board up. Okay. Let's go ahead and start pulling out the constant. So we have a constant there. We have a constant over here. We have a constant right there. This dq turns into linear density times dx, which the linear density, we can pull that out. Okay, we're left here with 2k r linear density, or lambda. Okay, right. Now we integrate all of it. So left with just the e, right? Okay. 0 to L over 2. Okay. We have 1 up top here. Let's not forget about that dx, but let's bring it out over here. Okay, and then we have these two parentheses that are inside. They're saying the same thing. Therefore, you can just add up the exponents here. So 1 plus 1/2 is equal to 3 over 2. All right. And yeah, this is it right here. We have derived the equation that will model this type of scenario. Okay. And if your calculator can do calculus, then you can just simply plug this in and get that answer. Also, lambda here becomes Q over L. Okay, very important. Let me see. Okay, so yeah, if you have a calculator that's able to do calculus, you can just you can just plug this into a calculator and you'll get your answer. Okay. Again here. Okay. You have your L, right? L is right here. Make sure to plug. Make sure to don't plug things into centimeters. Plug them in. Do the conversion. Get it to meters. Anything that's not in standard SI units, convert it to standard SI units. Once you do that, you plug into this equation, okay, and your output should be approximately 9.66 NC. All right. Yeah, that is the video. Yeah, you know. That's the video. Yeah, hopefully you've enjoyed it. There you go. Oh yeah, this answer there, that's the y component. Okay, because yeah, again the x component is 0. Right. Okay, there you go.